So this lecture is going to go into the discussion of correlation analysis. This image here on the screen is used to remind you that correlation and causation are not the same thing. It is a correlation that 100% of people who breathe will die, but it's a causation that 100% of people who don't breathe will die because they die of suffocation or of asphyxiation. Correlation analysis looks at the relationship between two variables. So, in all business fields, identifying and studying relationships between variables can provide information on ways to increase profits, methods to decrease costs, or variables to predict demand. We often begin our study of the relationship between two variables with a scatter diagram. It gives us a visual representation of the relationship between the variables. So for instance, we might have a sales manager who wants to know if there's a relationship between the number of calls made in a month and the number of copiers that were sold that month. And so you could begin the analysis with a random sample of 15 sales representatives. And then with this data, the number of sales calls would be our independent variable and the number of copiers sold would be our dependent variable. So using that information, we can develop a scatter diagram of the data. So on the previous slide, our first salesperson was Brian Viros. He made 96 sales calls and sold 41 copiers. So to plot this point, you would move along the horizontal axis to x equals 96 and then go vertically to y equals 41 and then place a dot at that intersection. You would end up doing this for all of your sales representatives. And then looking at this graph, it would be perfectly reasonable for the manager to tell the salespeople that the more sales calls they made, the more copiers they can expect to sell. Now, note that while there does seem to be a positive correlation between our two variables, all of the points do not fall on the line. And so when we're looking at that, we start looking at the correlation coefficient, which is the measure of the strength of the linear relationship between our two variables. When you're doing this, both of your variables must be at least on the interval scale of measurement. When you have a value of -1, that indicates a perfect negative correlation, and a value of +1 indicates a perfect positive correlation. And so if you look at this picture here on the right, you see the range from -1, perfect negative correlation, all the way to +1, perfect positive correlation, with 0 being no correlation in the middle. In the set of charts on the left, the first one indicates no correlation between the number of children as our independent variable and income as our dependent variable. The middle chart shows that there is a slightly negative correlation between price and quantity. And then the chart on the right is going to show a strong positive relationship between hours studied, which is our independent variable, and exam score, which would be our dependent variable. So going back to our sales data, drawing lines through the center of the data establishes our quadrants. And so these two variables would be positively related when the number of copiers sold is above the mean and the number of sales calls is also above the mean. Those points would end up being in quadrant 1. When the number of sales calls is less than the mean, so would be the number of copiers sold, and those points would end up appearing in quadrant 3. The correlation coefficient is designated by the letter R and is found using the equation of the sum of our individual x observations minus the mean of our x observations multiplied by our individual y observation divided by the mean of our y observations divided by our number of observations minus 1 times the standard deviation of my x values and the standard deviation of my y variables. And so you can get the standard deviation of the x and the y values very easily if you use the formula equals stdev dot s parentheses the range of cells that you're looking at in Excel. And so using our standard deviation values that we've obtained from Excel and the completing the rest of the equation, we find that our correlation coefficient for this set of data is 0.865, which, based on what we looked at on the previous slide, would indicate that this is a strong positive relationship. And so here we're looking at a scatter diagram with a positive relationship existing between age and profit, but it doesn't necessarily appear to be a very strong relationship. And so if we took into account our age and our profit, we could calculate that our R value is 0.262, which would be much closer to 0 than 1. And so therefore, we would observe the relationship between the age of the buyer and the profit of their purchase as not being very strong. We can look at the significance of our R value by testing the hypothesis that the population correlation, which is rho, is different from 0. And so let's look at this on the next slide. The population in this example is all of the salespeople employed by the firm. So this would be a two-tailed test. And so we're going to use our t-distribution to determine our statistic. And so we have n minus 2, so 15 minus 2 equals 13 would be our degrees of freedom. And since it didn't specifically say what significance level we should be using, we are going to assume that it's going to be 0.05 as my alpha value. And so then I'm going to use the t-test for the correlation coefficient formula shown here at the bottom of your slide to calculate the value of t to get a value of 6.216. Since 6.216 is outside of that range of negative 2.160 and positive 2.160, we're going to reject the null hypothesis and say that there is a correlation with respect to the number of sales calls made and the number of copiers sold in the population for the salespeople. Here we have another example where we're looking at the Applewood Auto Group. We found that our R value is 0.262, which is a positive but weak value. And so we're going to test our conclusion by conducting a hypothesis test that the correlation is greater than 0. So here we're really just wanting to know if this is a positive or a negative correlation. And since we're just looking at one direction, this is going to be considered a one-tailed test. And the degrees of freedom in this test is going to be n minus 2. So we have 180 minus 2 to get me 178. But our values on 178 aren't really available using the table that we have. So let's go ahead and look for 180 as degrees of freedom at the 0.05 alpha. And so we find that the critical value at this one is going to be 1.653. And so then we can use the formula that we saw on the previous slide, and we calculate a value of 3.622 and conclude the sample correlation is going to be too large to have come from a population with no correlation. And so therefore the outcome of a marketing campaign would be directed to older buyers is uncertain based on this example.